Hello, my name is Marcel Böhme, and I'm a faculty member at the Max Planck Institute for Security and Privacy in Germany. And this talk is about our ICSI 2022 paper in the near track on statistical reasoning about programs. So what is the program analysis problem? In program analysis, you have certain questions about properties of your program. Like, are there any bugs? Where are those bugs located? Do these pointers point to the same memory location? Or does there exist an input for which this program statement is reachable? Okay, so what is a program? A program consists of a set of instructions for the machine. So the programmer can tell precisely what the machine should do for a given input. Now there are programming languages within which you can write programs. And these programming languages come with a formal syntax and formal semantics. So the formal syntax describes the structure of all programs written in the language, while the formal semantics describes essentially the behavior of these programs. It describes exactly what the machine should do for each instruction. So then to formally reason about a program means to interpret its instructions according to the given semantic rules. So given the formal semantics. And two, to derive a model of computation that then describes the relationship between the inputs and outputs of that program. So the model of computation is essentially the machine's idea of what the program should do for all different kinds of inputs. And then formally reasoning means to compute the property of interest within this model of computation. So you're given the program source code, and using the semantic and syntactic rules, you derive this model of computation. And then you reason within this model of computation. So this was the vision that Tony Hoare laid out in 1969. And we should know that at this point in time, only really people in academic and research institutions had access to a computer. So the advantage of this approach is that we can analyze and then formally guarantee universal properties about this program that hold for all inputs. So we can prove the absence of errors. And we can analyze programs irrespective of the machine that is running on. Right? So you can reason at any level of abstraction, which allows us to implement very efficient program analysis techniques. But then there are also challenges in formal reasoning. One of the earliest undecidability results is that you can't really decide whether two pointers point to the same memory location. And here is maybe one of the most negative results in program analysis. Rice's theorem even says that all non-trivial semantic properties of programs are undecidable. So this is really a big problem. Many interesting program analysis problems are really undecidable. A second disadvantage of formal reasoning is that the model of computation may be incomplete or incorrect. Some code may only be available at runtime. So for instance, you have Java reflection, or in C, you can dynamically load new libraries. You don't have access to certain libraries. You only have the binary for those libraries. Maybe some code is written in a different language. So not everything that constitutes the runtime behavior of a program is available to the analysis. Also, even if we assume that the formal semantics for the programming language is available and the program is written only in that language, the compiler or the interpreter may resolve undefined behavior. So at these points, the compiler is at liberty to interpret an instruction in any way it wants. An example of undefined behavior is memory corruption when you read behind buffer in C, for instance. And another problem with model of computation being incomplete or incorrect is that the program analysis must make assumptions about the machine. And so here's a paper called Platform Independent Programs, where they write a single binary string that is valid on all three architectures, x86, ARM, and MIPS, but it behaves completely differently in all the three architectures. Right, so when you analyze a program and you build your model of computation, it must be with respect to a certain machine or assumptions about that machine. And of course, another maybe disadvantage for scalability, tool builders actually trade soundness or completeness. In order to scale program analysis to maybe the size of 2 billion lines of code, like in Google, you have to make compromises. And these compromises often come with reporting bugs that do not exist. This is the false positive problem, or failing to report bugs that do exist. This is the false negatives problem. So what the research community has then been trying to do in the last couple of years is, in an engineering approach, essentially try to patch up these false positives. So, okay, all of this is to say there's still a lot of achievement in practice, right? So what we know in theory might not hold in practice. In practice, we have found ways to deal with this. We have industry-grade static analysis tool like Google ErrorProne, like GitHub CodeQL, or Facebook Infer, which have found substantial success in finding bugs and security-critical vulnerabilities at scale. There's also another approach, formal verification, where you want to prove certain properties for all inputs. And there have been efforts to prove the correctness of an entire operating system microkernel. And there have been similar efforts in formal verification. Many of them had impact in practice. But for practical program analysis, there are really no guarantees. Right? So I told you about this gap between the model of computation and the actual runtime behavior of the program. And I also told you about this trade-off between scale and correctness, in a sense. Scale and soundness and completeness. Right? So no guarantees means we don't have soundness, we report bugs that don't exist. We don't have completeness, we do not report bugs that do exist. And so this was realized in the middle of last year in an article written by Wadi about program verification, vision, and reality. And so Wadi says, in retrospect, the hope for mathematical certainty was idealized and not fully realistic, I believe. And this is reflecting on Hoare's formal reasoning vision. So the problem now is that we can't even seem to quantify the degree to which our analyses are incorrect. As I said earlier, we're now developing techniques that kind of minimize these false positives, but we still do not have a handle on exactly how incorrect our analyses are. Right? So how many bugs do we not report? Or what is the proportion of false positives? And so here's the idea of statistical reasoning about programs. You start with a scale-oblivious, sampling-based in vivo program analysis. So scale-oblivious means it doesn't matter how large your program is, it just needs to be executable, and you can conduct your analysis. Sampling-based means you sample executions of that program and observe the property that you're interested in. And in vivo means you're analyzing the program in production while it is running and in an environment for which you want to make a claim or a statement about the runtime behavior of your program. You can distinguish two settings. One is the observational setting, where you simply observe your program property for a random sample of executions. And the other one is called the experimental setting, where you iteratively generate and validate certain hypotheses about your property by modifying and comparing certain copies of your random sample of executions. So let me give you an example for the experimental setting. In our team, we developed a tool called Mutaflow, which would identify information flow. So you have certain secret information, and you want to know whether the secret information ends up in a public thing, from the sensitive source to a public thing. So what we would do is we take an execution of the program, and for every executed sensitive thing, a sensitive source would simply fork the execution into a shadow execution. The execution in production would normally continue, but in this shadow world, we have this shadow execution, which continues with a modified sensitive data. Right? And if at any point in the execution we find a public thing, we simply check whether there's a difference between the shadow execution and the normal execution. If we see a difference, there must be an information flow. Okay, so this was an example for the experimental setting and for scale-oblivious program analysis. Now let's take this guarantee part back in. We'd call this statistical reasoning about programs. And it allows us to extrapolate from properties in the samples to properties of this entire population. And we can do that because of the statistical tool set. We can do that with quantifiable accuracy for systems of arbitrary size. Right? And if we need better efficiency, we need better scalability, we can always reduce the sampling rate, the number of executions that we are currently sampling per unit time. In contrast to static analysis or formal reasoning, the guarantees remain intact during the trade, right? So just to be clear, there are many statistical challenges to be tackled. I mentioned some of those in the paper and at the end of this talk. But this statistical perspective provides us with a new lens through which we can investigate the program analysis problem, particularly for programs at the very large scale. So statistics allows us to measure properties of the systems of arbitrary size, right? It doesn't matter how large a population is, we can still find quantities, parameters of that population. And then we can measure the degree of uncertainty about the facts that we have observed, right? We can be uncertain, and just how uncertain the result is that we get from the program analysis can be quantified. And this is the backbone of any statistical analysis. So why today? So I told you earlier that this idea of formal reasoning came back when only other researchers had access to a machine. Today, 1 million computers are sold every day. Today, we also have the technology. For instance, there's visualization and hypervisors. So you can run any software on any system, on any hardware due to this virtualization. Here's a talk excerpt from Kostya Seripiani in November 2022, where he explained that this bug finding technology, which is called GWP-ASAN, is deployed on all Chrome browsers, on all Google server-side applications, on all Android R phones, and soon in the Linux kernel. So this is bug finding in a very crowdsourced manner. And the idea behind GWP-ASAN is to sample executions and enable bug detection only for a sample of executions. And from those sample executions, we can then reason about executions across all machines. And because the Chrome and Android ecosystems are so large, even a very, very shallow signal enabling this analysis with probability of 0.00001 will still give enough signal across all the different devices. So technology, virtualization, hyperscale. We also have compiler passes. So we can take an arbitrary program and instrument those programs. This doesn't only work for compiler passes. We also have binary instrumentation, so we don't have the compiler. There are now also ideas to simply extend the operating system kernel. So every program that runs on this operating system kernel could be subject to bug finding or any other program analysis problem. And today we also have collaborations between software vendors and hardware vendors to kind of develop these hardware-assisted program analysis, like ARM memory tagging. So really, we have a lot of development in this new technology to observe program executions without actually implementing the program analysis into the program. And so this provides a lot of opportunities. Firstly, we can develop foundations of statistical reasoning about programs. The statistician can think about different problems in that we have in program analysis, like distributional shift. I'll talk about some of those problems later. And the software engineer can think about this scale oblivious analysis of programs that are heterogeneous and very large scale. And so developing these foundations is going to be interesting. And secondly, we are there's a lot of opportunity in integrating formal and statistical reasoning, both conceptually and also technically, to gain essentially the best from both worlds. Right? Formal reasoning allows you to reason about all inputs of a program, while statistical reasoning gives you this handle on the guarantees. And Of course, this allows us to develop very novel scale-oblivious program analysis techniques. And I'm really looking forward to the techniques that will be developed in the future. There are also challenges, of course. For instance, observation effects. When you actually modify the execution of a system in production, you might have some impact on those executions, right? When you measure a system, the measurement itself might have an impact on the system, and you want to minimize those observation effects. Then, of course, there are privacy concerns because we are handling information from an execution, and those executions might have been generated by a user. We don't want to leak this information through the analysis to someone else. And statistically, we can never be sure about something, right? So there's never something 100% certain. We can quantify the certainty, but I can already say for sure that nothing is 100% certain. So some things might just be improbable if we have never seen them. And another challenge, this is more statistical challenge, is that the operational distribution of a system might not be, that these samples from this operational distribution might not be independent and identically distributed. Right. So identically distributed means that every time I do a sample, every execution will have the same probability. But because systems change and users change, there could be some kind of some kind of distributional shift. And this can be analyzed. It's a problem in machine learning as well, problem in statistics as well. Definitely interesting to look into this in the future. Okay, so what did I talk about? I explained what formal reasoning about programs means. I explained what the problem of current approaches to formal reasoning about programs is, and that we can't really seem to quantify the degree to which our analyses are incorrect. And then I provided an opportunity to resolve this, to kind of win back the guarantees that Tony War started out wanting to have. And then I explained a few opportunities for this in the future and also a few challenges. So my personal belief is that statistical reasoning will become a part of the future of software engineering. Like in biology, what you can do when you analyze a large organism, you can model that organism and then reason within this model, and then make predictions about the behavior of the organism based on that model. This is called in silico. There are two other approaches in biology, and they are more widely distributed. They're called in vitro and in vivo analysis. In vitro is where you take the organism out of its normal environment, and then you would investigate the behavior of that organism within your lab environment. And in vivo means you look at the behavior of this organism as it is interacting with its environment. And this is the suggestion that I make here. We should look at software systems as interacting with it in the environment and as very complicated systems, and therefore employ in vivo approaches, and at the same time get some kind of guarantee about the statements that we make about the behavior of our programs. Thank you very much, and enjoy the rest of your conference.